Well, thanks very much, Tony, and thanks for the organisers for this mini conference. And so the author list is, as you can see, it's a bit on the long side. It involves Peter Hall, that many of you know was the first director of our Centre of Excellence, and unfortunately he passed away about 3 years ago. The last authors here in the room, this young man, James Yu, in the black shirt. And we've got a couple of people, Alan, I think, speaking later today, and Ian Johnston, who's at Stanford, John Ormerod at University of Sydney. So the problem I'm going to talk about is actually fairly close to home. Many of you would have seen this sort of situation in courses like applied longitudinal data analysis. So think of data sets like this, where you have repeated measures. Here, each panel corresponds to a different subject in some study involving toenail diseases or something, and the red and blue correspond to two different treatments. But the main twist is that the responses are binary. So that's the thing that causes a lot of headaches when you start doing analyses. And the main body of work is known as generalised linear mixed models. It's been around for a good 25 to 30 years, but even today, I would put it to you that we're still finding room for improvement, both in terms of methodology and theory. And this talk is still making what I would say is still inroads into new improved methodology and theory for analysing data sets like the one on the screen. The theme, of course, is massive data sets, and we do have a massive data set from the Red Cross Blood Service, 1.4 million records, 160,000 subjects. And if you want to find out more about that, talk to James during the coffee break. He'll tell you how it's going. So the model, again, it's something that's familiar to many of you. It's just the binary mixed model situation. You do have to choose a link function. And so if you choose the expert function, 1 over 1 plus e to the minus x, then you're doing logistic mixed models. But you don't have to choose that. You could say, I'd rather choose, the Gaussian cumulative distribution function, and that's called Probit mixed models. So you can choose which one you like, and we're going to sort of argue that the second one's a bit more convenient for the approach that we're going to talk about today. So anybody that's researched in generalised linear mixed models is familiar with this thing that I call the log likelihood integral headache, which means that when you have the binary response situation, you end up with an integral in possibly a high dimensional space. In the random intercepts case, then the integral is univariate, and so the main package in R, LME4, does use quadrature to get around it, but as soon as you end up with bivariate or trivariate integrals, then it says, no, I'm not going to do that. I'm going to just fall back and use Laplace Approximation. All right, so this is the standard software in R for handling this problem, but it can't properly handle more than random intercepts and univariate integration. All right, so the next two slides. So I gave this talk twice last year, once in Saudi Arabia, once in Singapore, and they're actually already dated. So this is actually new discoveries in this year, like in the last month since Christmas pudding about a month ago. And I'm going to have to correct myself in a few slides from now. So what I thought, even as early as last month, that Laplace approximation is not consistent or efficient, so that I'm not arguing with that. But Gaussian variational approximation, which John Ormerod and I developed back in the early 2010s, we got Peter Hall to prove some theory about it, and we thought that it wasn't fully efficient. And now we think that expectation propagation has ticks in every column. And so our 2011 paper with Peter showed that Gaussian variational approximation, which is quadrature-free, which is what we're aiming for to get around the integral problem, is consistent but not fully efficient. And allegedly, expectation propagation is fully efficient, and that's meant to be the main selling point of this talk. It's the first ever fully efficient integration quadrature-free approach for GL, generalized linear mixed models. Or so we thought. All right, so since Christmas pudding a month ago, I've been emailing with various California-based theoreticians, Jiming Jiang and Ian Johnson and so on, and we now think that this is the case. I wish I'd known this back when I was submitting to Annals in 2010 or whatever, so I could have said that we've attained the Crimea rail lower bound, we've got asymptotic full efficiency of our approach, but that paper doesn't claim that because we didn't know it back then, and we've only figured this out recently, and we're still trying to figure it out sort of rigorously, but we now believe that this is the current situation, or the situation. All right, so let's now go to some empirical results that support the claims that expectation propagation leads to fully efficient inference for generalized linear mixed models. So first of all, if we go to the main competitor, the one that's in software such as GLMER, Laplace approximation is such that you can see that a lot of the confidence intervals are too short. So the light blue one is what you're meant to get if you do things exactly with quadrature, and the dark blue ones are what you get if you use Laplace approximation, and they don't have the correct length, and you end up with the empirical coverage way below 95%, even though you're saying it's a 95% confidence interval. Expectation propagation gets you with the dark blue and light blue quite close to each other, and you are getting good coverage, and you're getting the advertised 95% most of the time pretty well. All right, I'm going to switch gears a little bit again now and talk about research silos. So what do I mean about research silos? So in some ways, conferences like this are sort of on the interface between statistics and machine learning. And that's really what this talk is about, because expectation propagation has most of its literature outside of statistics. You know, it's in areas like robot vision and machine learning and other computer science engineering type areas. And mixed models has most of its literature in statistical areas like biometrics and so on. So I did a quick search on the web of knowledge when I was getting the talk ready last March. And if you look at the main research areas that use the phrase expectation propagation, they're all in areas like computer science, telecommunications, image science, technology, and so on. And by the way, some papers have more than one category, so these are not mutually exclusive. And then finally, you get 8% mathematics, which is probably the few statistics papers on it. Then if we go inside the mixed model silo, we have areas like agriculture and ecology and public health. So really, there is this, two branches of literature aspect to this talk where the methodology has grown up in a different area than the applications that come up in statistics, such as genetics and agriculture. And then this is a little bit of an aside, but inside the mixed model area, it's taken me years to figure this out, there's all these other silos where, like, I spent 6 years at Harvard School of Public Health, and they have their terminology, but then I've realised that there's a social science silo and the sample survey and the econometrics panel data terminology and the psychometric. So they're all actually just doing mixed models with different phraseology. And if you're getting sick of looking at silos, this is the last silo metaphor slide of the talk. So we're taking all that nice grain in the expectation propagation silo and loading up the truck and shipping it off to the mixed model silo and sort of mixing it around and seeing what we get. All right, so what happens in the actual mechanics of getting frequentist expectation propagation to do mixed model type analyses? It turns out we can get it down to pretty much one page of mathematics. So here's a mathematical problem. You have a multivariate density function, P, that's proportional to F. Remember, that's like a CDF, like cumulative distribution function of a linear form, and that's multiplied by a multivariate normal. So that's my density function, right? I'm allowed to state that. And then I can say a problem that I want to solve is find the normalizing factor, find the mean, and find the covariance matrix. All right, so that's a legal mathematical problem that I can state. A key observation is that if I choose F to be the Gaussian CDF, then you can solve that problem exactly. All right? And so it turns out that there is closed-form integration results that allow you to do that. And so that form that I had a couple of slides ago where I had like the capital F times a Gaussian, that might look like this sort of skewed bivariate density in the two-dimensional case. And then if I now say find the mean and covariance for that density and the normalizing factor, and then find the Gaussian density that has the same mean and covariance matrix, I end up with that, right? So you might say, so what? Well, the thing is that you just have to do that, and that's about all you have to do. So once you've solved this problem of taking the sort of the input blue and then getting the corresponding Gaussian one that has the same mean and covariance matrix, then that's everything else is actually quite easy in terms of the computing. So there's one that's a bit more skewed again, and there's it's actually called the Kullback-Leibler projection onto the Gaussian family from the blue one to the red one. So in the accompanying paper that goes with this that I'll talk about later, in a typical example where we have, say, 6 fixed effects and random effects dimension 2, and we have 250 patients, say, and 25 measurements per patient, you do what I just went through with those red and blue projection things. You do it a lot of times. You do it about 1 million times, all right? But so that's sort of the sort of bad news. But the good news is that's all you need to do. So once you've got that down to a fine art and figured out how to do those projections, and we have figured out how to do it quite nicely, at least in the Probit case, then you don't have to do any other computing. Well, not much. So now, in terms of getting good practical performance for doing binary mixed model analyses, if you do a bit of quasi-Newton-Hessian approximation, program it in Fortran 77, which is the language that I learnt as an 18-year-old in 1982, and I haven't learned how to use C. And you get it running on my laptop that I bought 2 years ago. You can get point estimates and confidence intervals for all parameters in 18 seconds. And there they are. So that shows there's 9 parameters, and the coverages are all close to the advertised 95%, and each one of those only took about 18 seconds on my 2017 bought laptop. All right, so now what's the gains, if you like, from doing things exactly compared to doing things using expectation propagation? So if we have univariate random effects, then we do need m univariate numerical integrations and m times n projections. When you go to the bivariate random effects case, you need to get into bivariate quadrature, which isn't as much fun as univariate. But with expectation propagation, you're still just doing those projections. You're just doing bivariate projections, which you can do explicitly. And when you have trivariate random effects, you avoid the even more difficult problem of trivariate numerical integration by doing these projections. All right, I'm probably may skip over the next slide, but this is just some of the mathematics. Yeah, I'll just quickly, maybe I'll just spend like 20 seconds on it, but you have these various like Probit normal forms, and you sort of iteratively project them onto Gaussian forms, and you do it. So it turns out you're just doing sort of iterative moment matching over and over again, millions of times. So again, the problem that gets done millions or thousands and possibly millions of times is you have an input density function that looks like this, and you say, give me the matching multivariate normal one, and that can be solved exactly if the link corresponds to Probit. All right, now we're going to talk about how did I get those confidence intervals. Remember I said that I was getting, close to 95%. How did I do it? So we're going to just have a little bit of a thought exercise now. We're going to imagine that last night while you're sleeping, some evil fairies broke into your brain and they stole all your calculus rules, right? So they stole the chain rule, they stole the product rule, and they even stole the x to the n rule, which would come in handy for this. And what you have to do, given that that's what happened to you last night, you still have to find the second derivative at the maximum without any of those rules. All right? So how are you going to do it? And you are allowed to use your laptops that some of you have open in front of you, particularly if you've got R. So here's the solution. You could even try this if you've got your laptop running. But one solution is to just use the function optim. And the method is the so-called Broyden, Fletcher, Goldfarb, Shannon method. And you say Hessian is equal to true. And you hit enter and you get 22. And later on today you can prove that 22 is in fact, minus 22 is in fact f double dash peak. And you didn't use any calculus rules at all. All right? So you might say, who cares about solving this problem without calculus rules? I'd rather just use x to the n is n times x to the n minus 1 and so on, derivative. Well, that's all right in the univariate case, but when you're in 12 dimensions, it's a bit more challenging. And also, yeah, and you can't, we don't have calculus rules for expectation propagation. So when we use R's optim and Hessian approximation and confidence interval construction in 12 dimensions, so we're now trying to climb a 12-dimensional mountain just by doing function evaluations, and then when we get there, we say, all right, we're at the top of the mountain, now we need to find the Hessian, like a 12 by 12 Hessian matrix. Well, it turns out optim does it quite nicely for us, and we get 95% empirical coverage just by doing that approach. All right, just quickly, a lot of people like logistic regression because of things like odds ratios interpretations, and James has proven that it works. He did a simulation study on some cluster computer. It only took like 3 months or something, James, to run. And so it does work, but the thousands upon thousands of integrals that you need to solve that integral that doesn't have a closed form makes it much slower. And James and I are going to be back on this campus about a month from now. We decided that Ian Turner, I don't know if he's in the room, but Ian and us should compare notes given his numerical analysis expertise to see if we can push that boundary a bit further. And it's meant to be chief without a V. Yep. All right, so I realised that I'm giving a talk called Frequentist Expectation Propagation on like the main Bayesian statistics group in the country, and I thought I'd better like try to cover myself philosophically. And some people might say, didn't one like give a talk on variational Bayes when he was up here a couple of years ago? And like, is he a Bayesian? Now he's giving a talk on Frequentist. And the answer is, I'm not actually that dogmatic. Like, I'm just like a guy that likes doing maths and computing and the occasional data analysis, and I don't, I'm happy to help out the Bayesians on a Monday and a Tuesday, and the Frequentists on a Wednesday and Thursday. So the question is like, why not just become a Bayesian and use Markov chain Monte Carlo like Stan or something? Well, one answer is that I've even had like grant proposals from various Australian applied statistics groups that say we have to do it frequentist. We need p-values. We need confidence intervals, not credible intervals. Or other people that work in legal statistics say, oh, you can't say to the judge, I'm going to put this prior on my parameters, and then you have to like accept this as evidence. You have to like be a frequentist to get it past the jury in court applications. So I'm going to put it to you that, yeah, you can't just be a Bayesian totally. There's still room, there's still like many applications that demand frequentist inference. So that's the end of Philosophy Corner. All right. So just to start to wrap up, and I probably will be below my allocated 45 minutes. So a few slides on theory. And we're going to go back to a classroom type example. So we have x1 up to xn, which is normal, with mean mu and variance 1. And we've got two estimators, mu hat, which is x bar, and mu hat under tilde, which is x bar times 1 plus 11 over n squared, plus 7 tan h x1 over n cubed. All right, so which is the better estimator? All right, so no one knows. All right, so it's x bar. But here's the homework, which you're welcome to try later on today. We learn in class that mu hat is unbiased and fully efficient in that it attains the Cremier lower bound. Prove that mu hat under tilde is also unbiased and fully efficient asymptotically. All right, so who reckons they can prove that? All right, so the thing is that even today, 25th of January 2019, there's still room for doing maximum likelihood type asymptotic theory, and we are doing it with people in California. And so you have the juicy theoretical question. This is the estimator that I've spoken about this morning, and you can define estimators, but then you can say, is it fully efficient asymptotically? Like, can you prove central limit theorems and have like the lead terms correspond to the lead terms of the maximum likelihood estimators? And we're still dealing with this right now. We have, this work is actually part of quite a long journey, in some ways quite sad because it involved Peter. So it started way back in 2011 when I wrote Peter into this, and he did quite a lot of theory around the year 2012. And even just before he got ill in 2014, he and I were communicating about it. After Peter passed away, I got talking to Ian Johnston, and he's now working with us on it, and Song Mei is one of his students. This paper is dated 8th of April 2014, and we were getting close. I was hoping to wrap it up, but we did need Peter's expertise, and I wrote to him, but it was only a few weeks later that he got quite ill and never recovered. And then this is one of his last theorems, where he's proving a theorem about the discrepancy between the exact log likelihood and the expectation propagation one. And you can see all this very interesting Peter Hall asymptotic theory in the remarks. So I'll leave the theory there. I'll now talk about R, and many of you were here doing R exercises yesterday, and another homework for you today is to try our methodology in R, because James and I have an R package on CRAN, so you can download this whenever you feel like, particularly if you've got a laptop open with you in front of you right now, and try it out. And we even have a vignette. Yeah, if I had my own laptop, I could do a live computer demonstration, but I didn't hook it up. All right, so just to wrap up, so let's do the final checklist. Scalable methodology. We believe that this methodology does scale up to massive data sets like 1.4 million that we have for the Red Cross blood data. And numbers of, we have 160,000 subjects. Our simulation checks have shown excellent coverage of the confidence intervals. We've proven consistency. We're getting close to proving asymptotic relative efficiency, and we have an R package. Yeah. All right, so main references. So expectation propagation kind of goes back to a 2001 paper by Thomas Minker in a proceedings of a machine learning type conference, and although some people would argue that there was earlier ideas around before this, but leaving those arguments aside, it is, a 21st century, computer science piece of technology that is only just being sort of taken notice of in statistics, and I'd like to, think that there's a lot of mileage in it to be used in terms of solving important statistical problems, and my group and I have invested a fair bit of effort into that in the last few years. All right, well, thanks very much.